These are our planned objectives for today. We'll be looking at data types, measures of position, normal distribution, and data transformation. Okay, so talking about data types, in analytics, it's very important to pay attention to data types. Data exists in different forms, different formats, in different forms, okay? Generally speaking, data may be classified as follows. Okay, we're looking at standard data types. We have categorical data, and then we have numerical data. I believe we are used to this already. Under categorical data, we have the nominal data, we have ordinal. Then under numerical data, we have discrete, continuous. Under continuous, we have interval and ratio data. Categorical data, nominal data is descriptive data. Okay, descriptive data that is descriptive in nature, like large, small, medium, different colors like yellow, blue, those kind of things. Those are descriptive. Okay, those are descriptive data. Ordinal data is ordered data, like ranked data. That's ordinal data. Under numerical data, we have whole numbers, otherwise called integer. Those are discrete data. Then we have continuous data. Under continuous data, we have the interval and the ratio data. Ratio data has absolute 0. Interval data does not. Okay. I believe this is more or less revision for those of us that are in class right now. So, measures of position. We also look at measures of position. Why are we looking at measures of position here? Because we have basically talked about the other standards measures in an earlier class. We talked about measures of central tendency and measures of dispersion or measures of variability. We also have measures of position. A measure of position determines the position of a single value in relation to other values in a sample or a population data set. Unlike the mean and standard deviation, which is a measure of central tendency, and standard deviation, which is a measure of variability, descriptive measures based on quantiles are measures of position, are not sensitive to influence of a few extreme observations. I tried to demonstrate that last week when I tried to, when we're comparing median and mean. Okay, so we demonstrated the fact that extreme median is not very sensitive to extreme values. Okay, extreme values are the extremes. Okay, so I think we demonstrated that. Now, measures of positions are like that. Median, even though it's classified as a measure of central tendency, median is also a measure of position. Why? Because Median is also a quantile. Okay. For example, we have first quartile, second quartile, third quartile. Second quartile is the same as median. Quartiles are measures of position. So since second quartile is median, so median can actually also be taken as a measure of position. And that explains why it is not sensitive or less sensitive to extreme values. The commonest measure of position are percentiles, quartiles, and standard scores, also called z-scores. Percentiles, quantiles, and z-scores. Okay. So percentile is when the um, values, after being ordered, are split into hundreds parts, 100, 100 sections. Quantile splits values into 4 parts. Okay, 4 equal parts in terms of quantity. Okay, and z-score is based on normal distribution, which we will see shortly, which we'll look at shortly. Okay, the normal distribution. In data analytics, the normal distribution is very, very important. If you are a data analyst, you must have some idea, at least some idea of the normal distribution. Okay, normal distribution, also known as the Gaussian distribution, is a probability distribution that is symmetric about the mean. It is symmetric about the mean, showing that data near the mean are more frequent in occurrence than data from far from the mean. When we say it is symmetric about the mean, do we understand what that means? What do we mean by?
Please kindly explain.
Okay. What that simply means is, this is the normal distribution now. Okay. What that means is, if you are to cut it, usually the mean is at the middle here. Okay. The mean is at the middle. So if you are to split this curve, if this curve is split, okay, through the mean, the left-hand side and the right-hand side will be exactly equal, the same. Okay, so the left-hand side will be a sort of mirror image of the right-hand side. You can see the shape yourself. You can see that if you are to cut this through the center here, the right and the left side are exactly the same. Okay, that's what is meant by being symmetric about the mean. The mean is at the center in a normal distribution. In fact, mean, median, and mode, they are all at the center. Okay, we'll see all that shortly. Okay, so in graphical form, the normal distribution appears as an inverted bell curve. If you look at it, it looks like a bell that is turned upside down. Okay. If you were to draw something here, that would look like the handle of the bell.
Yeah.
Yeah, it looks like a bell. So that's why we say it's bell-shaped. It's a bell curve, bell-shaped curve. Points to note about the normal distribution. The normal distribution is the proper term for a probability bell curve. Okay, so that curve you saw just now is the normal distribution. Let's say something more about this curve. Now, what this curve means is Charles still with us? Charles, am I audible?
Yes, sir. I'm here.
Okay, okay.
Yes, sir. Yes, sir.
All right. So what this
Right.
what this curve actually tells us is that because the mean, median, and mode are the center, right? Let me see if I can get, I have another picture that will show that. Okay. Anyway, the mean, median, and mode are all situated at the center here, right? It's at the center. For example, if you look at this curve now, the mean of this data captured here is 175 cm at the center. The median is 175 cm. The mode, 175 cm. So the mean is at the center. The values to the right of the curve are higher than the mean. The values to the left of the curve are lower than the mean. Okay, that's the nature of the normal distribution. That's why we say it is symmetric about the mean. Okay. Then if you look closely, you see there are other features you can see here. You see, this is the normal distribution, but there's also what we call the standard normal distribution. We will come to that so that then I will explain why we have 0, 1, 2, 3 here. Then -1, -2, -3. What is the significance of all this? I will explain that shortly. Well, the points to note for now: one, the normal distribution is the proper term for a probability bell shape, that shape you saw just now. The normal distribution, the mean is 0. Let's say in a standard normal distribution, the mean is 0 and the standard deviation is 1. It has 0 skewness and a kurtosis of 3. Okay. Meanwhile, I know we've not talked about skewness and kurtosis. Okay, but what that is simply saying is if skewness is 0, what that simply means is the data is not skewed, it's not bent to one side. It's not skewed. Okay, skewed data is not like this. It's you see it bent either to the left or to the right. So that's it. So because of course we say it's symmetrical, the fact that it's symmetrical shows that it is not skewed. In other words, skewness is 0.
0.
Then kurtosis is 3. Kurtosis it measures the when the curve is very steep, okay, we say it has high kurtosis, or when it's low like this. The kurtosis, although that's not the proper definition of kurtosis, but to make it easier to understand for now, let me just explain it like that for now. Okay, but when we get to that, the topic, we'll deal with it in more details. But for now, the idea is that while skewness tells you whether whether the distribution is bent to the left or to the right, kurtosis will show you whether the distribution is compressed or tall or high, whether it's the top is flat down or Okay, even though that's not really the technical definition, but don't worry about that. But that's a simple way of visually checking if a data has high kurtosis or low kurtosis. But we are going to do kurtosis and skewness as a topic, so let's not bother about that. Okay, but for now, let's know that the normal distribution has a skewness of 0 and kurtosis of 3. So kurtosis higher than 3 is high kurtosis. Kurtosis lower than 3 is termed low kurtosis. Normal distribution is normal distributions are symmetrical, but not all symmetrical distributions are normal. Why is that? Now, the fact that a distribution is normal, is symmetrical, does not automatically mean it is normal distribution. Why? Because normal distribution also has other properties. It's not just the symmetry that makes it normal distribution. Okay, it has other properties. For example, we have already seen that in a normal distribution, the mean, median, and mode lie at the center, and they are the same. Okay, that may not be true for all symmetrical distributions. Okay, also we know the standard deviation, the way the standard deviation is um, structured with respect to the curve is another thing, okay, that is unique about normal distribution. Like here, you can see that the data between the data that fall between the -1 standard deviation and 1 standard deviation is about 68.2%. Okay, and just you can see all these are properties of these are properties of normal distribution. You can see between -2 standard deviation and +2 standard deviation covers about 95.4% of the entire data. Then between -3 standard deviation and 3 standard deviation encompasses 99.7% of the data distribution. So these are properties, these are unique properties of the normal distribution. I'm just saying, explaining all that to underscore the point that, or the fact that that a distribution is symmetrical does not make it automatically normal. And it should be noted that most naturally occurring phenomena tend to approximate the normal distribution.